Let's try to solve this problem here. When a dielectric is inserted between the plates of an isolated charged capacitor of capacitance 40 millifarad, the dielectric reduces the electric field in the capacitor by 20%. Okay, so let's draw a simple diagram to illustrate how does the capacitor changes from its initial state to its final state. Okay, so initially you have your dielectric is inserted between the plates of an isolated charged capacitor. So initially it is already isolated, it is charged already. Okay, so let's draw a capacitor. Okay, initially there will be a capacitor. Okay, so because it's charged, then we'll put probably one plate as positive plate, one plate as negative plate, means by it's already charged. And because the dielectric is inserted, that means by initially there is no dielectric. Initially in between the plates it will be a vacuum. Okay, so because it's a vacuum, we'll call the capacitance at that situation to be C0. Okay, usually the naught is for the situation where you don't have any dielectric in between. Whereas if you remove the naught, C only, then there will be the situation where the dielectric is already inserted. Okay, so for this case, there's no dielectric, so C0. So our capacitance is equals to 40 millifarad. 40 times 10 to the power negative 3 farad. Okay, so it's isolated. Isolated means by there's charge already. You are not going to connect it to any circuit. Okay, if you are not going to connect it to a power supply, you are just leaving it as it is isolated. Okay, let me explain why it's isolated. So if you charge a capacitor, usually you need to connect it to a capacitance, a capacitor resistor circuit, or an RC series circuit. Okay, so this is how you charge a capacitor. So right now, because you can see that this capacitor is connected to a power supply, connected to a resistor, there's charging process happen. So probably at the end of the charging process, you see that it's let's say fully charged, let's say. Okay, so the idea of isolated means by you are going to remove any connection to the capacitor. So if you remove any connection to the capacitor, the charge still remains, but you can see that essentially there is no path for you to move the charge from one plate to another. You can think of it as either the positive charge cannot move to the negative plate, or you can think of it as the electron cannot move to the positive plate, because there's no pathway to do so. So in this case, what we can know is if it's isolated, we know that the charge cannot change from its initial state to the final state. The charge can never change. So you know that Q0 is the same as Q. Okay, your Q cannot change from initial to final. Okay, so let's sketch the final situation where you still have the same capacitor, but right now there is dielectric in between them. Okay, I'm going to label the dielectric with another color, maybe in green, saying that in between these two plates there is dielectric inside it. Okay, I don't know what's the C, I don't know what's the capacitance now, the new capacitance. I don't really have the value, but I know that this electric field in the capacitor has been reduced by 20%. So now we are only left with 80% of the original electric field. So we are left with 80% of the original electric field, means by the E for the final situation is only 80% of the E of the initial situation. So that's 0.8 or 80% of E initial. Okay, so that's what we know regarding this situation over here. I think I've extracted everything I need quite clearly. Okay, so now let's try to solve the question over here. The question is interested to know the new capacitance of the capacitor. Okay, so we are interested to know the new capacitance, and we actually know that the new capacitance and the old capacitance, they are related through this relationship over here, where the capacitance with dielectric divided by the capacitance without dielectric will be equals to the relative permittivity or the dielectric constant. This is what we know. Okay, but how do we relate this information, this knowledge that we know, with the information that the electric field is equals to 0.8 of the initial electric field? We know that this capacitance here is related with the amount of charge stored divided by the potential difference across the capacitor. This is what we know. And of course, we also know that the electric field is related to the potential difference through V over D. Okay, so this is from chapter 1, okay, and actually the idea, it was delta V, but right now when we enter chapter 2, potential difference, we just represent it with a V. It's no longer delta V. Delta V is usually for chapter 1 electrostatics. So the delta V that we learned in chapter 1 will be replaced by V, which is still essentially potential difference. It is not electric potential, it is potential difference divided by the distance between the potential difference. Okay, so this equation here relates between the potential difference and the electric field. Electric field is given, we can relate it to potential difference. Then once we related it to potential difference, we can relate it to the capacitance, which is the knowledge that we have learned recently. Okay, so we can change C here to become the capacitance to be Q over V, whereas the capacitance without dielectric to be Q naught over V naught. So that is the relationship that we can obtain by bringing this into the equation. Then we know that for isolated case, Q naught will be equals to Q. So what we know Q naught and Q are the same thing. We can cancel them out. Then, sorry, I forgot the naught over here. Okay, there's a naught over here. So right now, if you rearrange the equation a bit, you get V naught over V is equals to the dielectric constant. Okay, V naught and V, we are already halfway there. Now we want to relate it further to the electric field, which we know the relationship between initial and final here. So we can further, let's manipulate this equation first. V is equals to ED. Okay, so this one means by you have E initial or E without dielectric multiplied by D without dielectric, E with dielectric multiplied with D without dielectric. Okay, we know that this D here is the distance between the two parallel plates over here. So this one is D naught, this one is D, but the question never really mentioned that we change the distance between the two plates, right? So essentially what it means is that D naught here will be equals to D. We do not change the distance between the two plates, so these two can actually cancel out. Okay, so now you are left with E naught over E is equals to the dielectric constant, and you know this relationship, E is equals to 0.8 E naught, so you can replace the new electric field or the electric field with dielectric to be equals to 0.8 electric field without dielectric. Okay, so right now you can cancel out the E naught once again, then you are left with 1 over 0.8. Then from there you can find out that, okay, I'll continue it over here, the dielectric constant, okay, it's equals to 1 over 0.8 and it's 1.25. Okay, and actually I take a slight peek upwards and I see that, oh, what is the dielectric constant of the dielectric? Well, this answers the question. Okay, but we know that we can bring this value 1.25 here back into the equation to find our capacitance with dielectric. Okay, so let's do so. So C over C naught is equals to 1.25. So we know that C naught is 40 times 10 to the power of negative 3 is equals to 1.25. So from here you can find that the capacitance with dielectric, this one is with dielectric, which is for this situation here. With dielectric, the value will be equals to 0.05 farad. Okay, so this is what we can do for now. Okay, next question B, they ask for the dielectric constant. Well, we already have the answer, it's 1.25. I accidentally flipped the order of me determining an answer, but I don't think that's an issue. Okay, so let me just keep it simple and write the answer back. Okay, question C, what is the permittivity of the dielectric? So permittivity of the dielectric, it's different from dielectric constant. We have to be very clear with these two things. Okay, the relationship between all these things will be the dielectric permittivity of the, sorry, I have to be very clear with this, cannot make mistake. Okay, the permittivity of the material or the permittivity of the dielectric, it's this epsilon symbol over here, is equals to the dielectric constant multiplied by the permittivity of free space. Okay, so this is the permittivity of vacuum or of free space. Okay, let me just write vacuum because it helps our understanding. Okay, so essentially you can think that because this is vacuum, this one, the permittivity will be E naught. Okay, so your dielectric has a certain multiplier. Okay, you can think of it as dielectric multiplier. Okay, it helps you to improve the permittivity by how much. Okay, you can think of dielectric constant like this. Dielectric constant tells you that this dielectric will help you improve the permittivity of the space by how much. Let's say improve by twice. Okay, the permittivity will be twice better than previously. Okay, than the previous situation, or it will be 3 times better. Okay, so the multiplier effect is what we name as dielectric constant. So this one is the dielectric constant. Sometimes you also call it as relative permittivity. Okay, because it's relative to the vacuum. With respect to vacuum, how many times does it get better? Okay, so that's why I call it as relative permittivity. Okay, permittivity. I'm not sure whether the spelling is correct or not. I know there's double T somewhere, not sure which place. Okay, then what comes out here will be the dielectric's permittivity itself. Okay, this one is the permittivity of the dielectric. TVT of dielectric. Okay, so it tells you the dielectric itself, how good does it permit. Okay, so you can think of the initial situation, it's the vacuum's permittivity, but because you insert a dielectric, the dielectric improve a permittivity by 2 or 3 times, or how many times, it depends on this value, 1.25 then in this case, then essentially the permittivity improved by 1.25 times. So that's a new permittivity of that space, or we call it as the permittivity of dielectric. Okay, so right now we are finding this permittivity of dielectric. We know that it's 1.25 multiplied by the permittivity of free space or permittivity of vacuum, which is in this case 8.85 times 10 to the power of negative 12. So from here, if we do our calculation, we see that the permittivity of this dielectric here will be 1.106 times 10 to the power of negative 11 farad per meter. Okay, so that's a unit for permittivity. Okay, so we have to be very clear that over here the main relationship is that the capacitance with dielectric is improved by this value, which is the dielectric constant, compared to capacitance without dielectric. Okay, capacitance without dielectric improved by this much, become the new capacitance with the dielectric inside. Okay, the permittivity when it's vacuum is this much, but it will improve due to the presence of dielectric by a certain factor, and that factor is epsilon r, or the dielectric constant. Then finally, what's the permittivity? Will be just this epsilon sign over here. So this is the relationship that we are using to solve this question over here. That's it for this question. Thank you very much.